Alright, this is an explanation of binary search. So consider this example. Hold on. Oh, this is a... There you go. Let's say we have nums equal to 1, 2, 3, 4, 5. And target, let's say it's 2 or something. So we're going to have some pointers. The pointer to the leftmost part of the range of the array, and a pointer to the rightmost element of the array, and this array is sorted. So what we're going to do is we're going to look for 2. We're going to look at the element in the middle and see if it's larger than, to see where it is relative to the target number. In this case, it is bigger. So the element at M, which is halfway between L and R, is larger than 2, which is what we're looking for. So we go ahead and move this pointer to before M, to 1 before M. And we repeat the process. So M is now here, and we, the middle point is between these two numbers. We just kind of round off to the left side. So we see that the element at M is smaller than the target. So we go ahead and move the leftmost pointer to 1 past M. So now we have found M. So we just return M, which is the index 1. So let's code that up, and I'll go over some other cases as well. So here we are. Let me just do that. I will do it this way. Let's see. I'm going to let's do a nested function. Let's do it like this. Be search, yep, like that. Nums target. So first we initialize L to the beginning of the array, like that. And R is obviously initialized to the end of the array, which is this. Then we're going to do this repeatedly. We're going to loop. Let's keep it like this for now. And the first thing we're going to do is we're going to compute M. M is just the midpoint. So, and it's going to be the average of the 2 of L and R because it's the middle. And we're going to round down. So as we discovered, so here M is larger than, the element at M is 3, that's larger than the target, so here's how we do that. Nums M is larger than the target. And what do we do there? We move R to 1 before M, like that. So that would be like this. And so now we loop again, and now M is here. We see that the element at M is smaller than the target, so that's this case right here. L if nums M is smaller than the target. And what we do is we move L1 past M, like this. So that's what we do. L is equal to M plus 1. And then we loop again, and we recalculate M. L and R are at the same place, so M is just right here. So we found it, and so we just, in this case we found it. So the else branch is when we found the element. Basically, the element at M is equal to the target, so we would just return M at that point. So we obviously don't want to iterate repeatedly. So when do we, let's say we have, I'll just choose a smaller array. Let's say we're looking for something that's not even in the array. So we're looking for 4 and the array is 1, 2, 3. So we compute m, which is here. Then as the algorithm says, with this line 2 is actually smaller than 4, so we're going to move L forward like that. We loop again because our loop condition is just true. So m, we can recompute m goes here, like that. And so we see that the element at m, which is 3, is still smaller than 4, so we push L forward and it goes out of bounds. So yeah, I mean, basically L has gone past R. So as long as L has not gone past R, we're going to keep looping. And if we haven't found anything, then we just go ahead and return -1. So that would just be this, return v search nums target. Let's test it on, well, this example, at least our own example. So run code. So it works on that one. Let's try it on this one. So target is 2. Works on the examples. Let's, what happens on an empty, let's say nums is empty. Then we never even enter this loop and we just return -1, so that should be fine. Let's try an empty array. Okay, so that's just not a valid input. 3. That's fine. 2. That's fine. Let's try 0, something smaller than 2. And I'll just submit it. And we're good to go. This is the code. And there you have it. That's binary search. The time complexity is O of log n, because on each iteration we're having the search space. You know, we took the middle and we're deciding which side contains the number. And in terms of space, it's constant because we're only using a handful of variables. And we don't allocate more space just because the input's larger. So there you have it. Enjoy.